Alright, welcome back. So this is our second day during the 2019 NCOV quarantine. We've got two main objectives today. The first one is I want to look at the difference between the formal definition of a derivative and the limit definition of a derivative, and we'll solve some limits involving both of those. And the second one is more dealing with curve sketching. So I want to be able to analyze graphs using relative extrema, critical points, points of inflection, concavity, and slope. Okay, so starting out with our definition of a derivative. The idea here is if we have 2 points, so I've got 2 points here, x fx and x plus a little bit and f of x plus a little bit, then our slope would be our change in y over change in x, or my y2 minus my y1. So that's y2 minus y1 over my x2 minus x1. So here's my x2, x plus delta x, minus x1. Okay, so if I simplify, my x and my x can cancel, so I'm left with just this for my slope, y2 minus y1 over change in x. If I wanted to get an instantaneous slope, then I could take the limit as my change in x approaches 0. That change in x is my difference between the 2 points. If that difference becomes 0, then I have 1 point instead of 2. So I could say that my derivative is equal to the limit as my change in x approaches 0 of our slope, which in function notation is x plus dx minus f of x over dx.
Hello.
Hello. Glad you could join us.
Yeah.
So I've been stalling just a little bit, but we went through the formal definition of a derivative, just the formula. So you guys
Okay.
are both strong on the formula part. I do want to take a look at some actual limits though, because on the midterm we kind of struggled with using it, even though we were able to get all the formulas. So here's 4 problems that are a little bit obscured. I'm going to work the first one out, and then I'm going to call on you guys to help me out with the other 3. So for this one, I've got the sine of 5 pi over 6 plus h minus 1/2 over h. So this is in my formal definition of a derivative, and I know that because if my function is the sine of x, then my x value would have to be 5 pi 6, and the sine at 5 pi 6 is 1/2. So this 1/2 is the sine at 5 pi 6. Okay, so what that means, let's see if I can zoom here. Nope. Okay, so what that means is my function of x is sine x, so my derivative then would be cosine x, and my derivative at 5 pi 6 would be the cosine at 5 pi 6, which is what?
Uh, 1/2.
The sine at 5 pi 6 is 1/2, so what should the cosine be?
Root 3 over 2.
Okay, that's the magnitude, but then for cosine, this will be back here somewhere, so...
Oh, negative.
Negative root 3 over 2, perfect. Okay, so again, because this is the definition of a derivative, that should be our final answer. Okay, so I'm going to take a look at this one. Same idea for number 2. If our function is cosine, then this root 3 over 2 should be the same thing as what?
Mm.
What's my x value right now?
1/2.
5 pi over 6.
For number 1, my x value is 5 pi over 6. I'm looking at number 2 right now, though.
Oh.
What's our x value for number 2?
X
Pi over 6.
Pi over 6, okay. Okay, again, my formal definition of derivative is x plus delta x. So this inside part of my function here is actually telling me my x value. Since our change in x is h, this is x plus delta x, or x plus h, which is pi over 6 is my x value. Okay, so my function is cosine. My function of x is cosine. Then, Junho, what's our derivative?
Negative sine x.
Negative sine. Okay, so what's this limit equal to then?
1/2.
Okay, so my sine at pi 6 is 1 over 2, and then I've got the negative on the outside here, so this will be negative 1/2. Okay, moving on to the next one. Oliver, what's my function right now? So what's the action that I'm doing to my x value?
Negative 1/3.
Negative 1/3 is the x value, but what's the action that we're doing to it?
Oh, 1 over 243.
Close. Okay, so I'm going to jump back
Um,
to number 2. My x value was pi 6. The action we did to it was we took the cosine. So my function was cosine x. What's my function for number 3?
Hmm.
Okay, for number 1, our function was sine x, so I was taking the sine of my x value. So this is x plus delta x is one x value. 5 pi 6 is my other x value. So this is really my function of x plus delta x minus my function of x, right? Over my change in x.
Yes.
Okay, I need to know what my function of x is down here. So what are we actually doing to the x value? Junho, if you
We
see it.
subtract 1 over 3.
The 1 over 3 is the x value. So this is x plus delta x. Okay, what am I doing to the x plus delta x?
Fifth power.
Raising it to the 5th power, right? Okay, so my function of x is x to the 5th power, and I'm going to double check. If my x value is negative 1/3, then this term should be minus negative 1/3 to the 5th power, right? Okay, so 3 to the 5th power, I've got 3 is 3 to the 1st power, 9, 3 to the 2nd power, 27, 3 to the 3rd power, 81, 3 to the 4th power, and 243, 3 to the 5th power. Okay, that would be a negative, and if I'm subtracting a negative, I would be adding a positive. So I am in the formal definition of derivative, and this is negative 1/3 to the 5th power. Okay, so my function of x is x to the 5th power. Oliver, back to you. What's our derivative?
5x to the 4th power.
Okay, and we're going to plug in our x value. What's our x value?
Negative 1/3.
Negative 1/3. Okay, so I've got 5 times negative 1/3 to the 4th power. What's negative 1/3 to the 4th power?
Is there an easy way to do it? I don't know.
I guess I've got these memorized now that I've done them enough, but you're just multiplying by 3 4 times. So,
3, right?
okay, so I've got
27,
mm,
6, 0, 83,
81.
81,
81.
81.
Okay, 5 over 81. Let me see if I can come up with an easier way to do that. Okay, this is 5 over 3 to the 4th power. 3 to the 4th power is 3 squared squared, right? What is 3 squared?
Yes. 9.
9. So that's 9 squared. What is 9 squared?
Oh, 81.
81. Okay, if that's easier for you, we can always break it up like that. Okay, cool. Any questions on 1, 2, or 3?
No.
No.
Okay. Junho, over to you. What is our x value for number 4? And then what do you think our function of our x value is?
4 and root x.
Perfect. Okay, we got it. So if my function of x is the square root of x, then what is f prime of x?
1 half x h the x negative 1 over 2.
Perfect. 1 half x to the power of negative 1 over 2. I'm going to simplify that really quick. So this is f prime of x is 1 over 2 square root x. Okay, I moved it to the bottom because this is a negative exponent, and I took the square root because this is 1 half. Okay, and I can plug in my x point now, and then we're done. So my x point was 4. So this is 1 over 2 root 4. So what's our final answer?
1 over 4.
1 over 4. Okay, so just to check, make sure this is in the definition of a derivative. If it is, then this should be f of x. So if I plug in 4, I get the square root of 4, which is 2, which is okay. So this is the definition of derivative, and my final answer for this limit will be 1/4. Okay, Oliver, any questions on anything?
No, it's fine now.
Okay, cool. So these are a little bit tricky because we're not already in the form for the definition of a derivative. That right side doesn't look like it's the right function. So my cue for this is anytime you see a value that's pulling to 0 and you've just got that variable on the bottom, I would keep the formal definition of a derivative in mind.
Okay.
Usually on the AP exam, they'll stick to h's. If they don't, then it's delta x usually for formal definition of derivative problems. Okay, so I've got Oliver answers one more time. Okay. In addition to our normal definition of a derivative, what I have down here is also called the limit definition of a derivative. Okay, it's really, really similar. So this time, instead of defining one point as x fx and the other point is x plus some change in x and x plus some change in x, I'm just going to call these 2 points with 2 different x values. This is cfc and x fx. Everything else is the same. So my slope is still change in y over change in x is f of x minus fc over x minus c, and I can still take my limit in order to get my derivative. So that's limit as x approaches c is y2 minus y1 over x2 minus x1 is my derivative. Okay, so what's happening is I am actually moving this point now closer and closer and closer to the other point. as long as x moves closer to c, then eventually x will get infinitely close to c, and we'll be taking the slope at 1 point instead of 2. Okay, here's our final form again. Any questions on the limit definition of a derivative?
No.
No.
Okay, cool. Alright, I'm going to quickly review all of our curve sketching stuff one more time, and then we'll take a look at a couple free response questions. So here I've got a quick chart. Everything on this side has a negative slope. This is a positive slope. This is positive concavity and negative concavity. Okay, so our first derivative talks about whether a function is increasing or decreasing, right? So for both of these on the left-hand side, my function is going down. So we know our function is decreasing, and my slope, that's my first derivative, should be negative. For both of these on the right side, my y value is going up, right? So my function is increasing, and my first derivative should be positive. However, how these functions are going up are slightly different. The difference is in our concavity. If you're thinking about physics, then that would be our acceleration, versus the slope is usually our velocity, if we're deriving a displacement function. So if our second derivative is positive, then you can think of that, if we're talking about displacement, that would be our acceleration. Your second derivative in terms of time would be positive. So my slope is decreasing. My slope is negative. But if you're concave up, then even though your slope is negative right now, your slope is getting closer and closer to 0. So here it is again. My slopes are negative for this one, but as we keep going, the slopes are getting less and less negative. So my slopes are negative, but they are increasing. If I'm going concave down, my slopes are negative, but they're getting more and more negatives. My slopes are negative and decreasing.
Okay.
On this side, my slopes are positive. Slopes are positive, but they're getting more and more positive as we go. If I am concave up, so my slopes are positive and increasing. On this one, my slopes are still positive, but they're getting less and less positive. So my slopes are positive and they are decreasing. Okay, any questions on what's going on with this slide?
No.
Okay, I'm going to give us an example really quick. So in real life, if we said our function is height in terms of time, so let's say we've got an airplane, so something that looks like this. Okay, and we're gonna we'll drop a buoy from the airplane. So that buoy is gonna go down into, I'll call this the water. So 3D. We drop a buoy into the water. At the point where it hits the water, our height is 0, right? Okay, up until that point, our height was decreasing, so that means we were falling, and our slope was negative. And our acceleration was also going down, right? Because of gravity. So as the object is falling before it hits the water, acceleration is negative, that's our acceleration due to gravity, and we're decreasing. So we are concave down and decreasing, which would look like this one. Concave down and decreasing as the object falls towards the water. Okay, once we hit the water though, our acceleration changes, because now if we have an object that floats, our buoyant force will be stronger than the force of gravity. So our acceleration suddenly changes from being negative to being positive. So even though our object has a lot of velocity, and so it's still going to be going down for a while, because the acceleration is positive, the speed at which it's falling is not as fast, right? We're slowing down because our acceleration is in the opposite direction of our velocity. Okay, so for this part of the graph here, my acceleration is positive, but my velocity is negative. So that would look like this one. We've fallen into the water. We're still falling in the water, but the water has a buoyant force that's pushing us up.
Yeah. Okay.
Okay, then we'll hit a point where our vertical velocity hits 0. We know it has to hit 0 because we changed from going down to going up. So if our velocity goes from negative to positive, there has to be a point where the velocity is 0. So after that point, the velocity becomes positive. We start rising and going back to the water. Now my acceleration is positive and my velocity is positive, so my speed is actually increasing, right?
Yes.
So that would look like this one. My velocity is positive and my acceleration is positive. Okay, if we got so much speed coming out that we actually break the water and keep going, so like bounce up a little bit, then after we clear the water, gravity takes over again. Now our acceleration is negative again, so we've got a little bit of vertical velocity because we popped out of the water, and gravity is going to pull us back down. So now we would look like this last one. Okay, any questions on what happened?
No.
Okay. Alright, then I'm gonna quickly go over some vocabulary, and I think we've got time for one free response. Okay, so critical points. A critical point is any point where the first derivative is 0 or undefined. For critical points, it does not matter if the slope changes or not. If the slope could possibly change, then it's okay. For a point of inflection, we're looking at our second derivative, not our first derivative. The second derivative could be 0 or it's undefined. But as for a point of inflection, the concavity must change. If the concavity does not change, it does not count as a point of inflection. Okay, so we've got more conditions for our point of inflection than we do for our critical points. Okay, then when we're looking at our...
So what's the difference between a critical point and points of inflection?
So our two things. The critical points look at our first derivative, where the points of inflection look at our second derivative.
Okay.
So if I draw really quick, I've got a
Okay, I see.
critical point here and here for this function that I just drew, because my slope is 0. For my point of inflection, I would have a point of inflection here when my acceleration is 0, because here I'm concave down, so that means my second derivative is negative, less than 0. Here my second derivative is greater than 0, is positive, so there has to be a point where we changed, right?
Yeah.
So
Okay.
because we changed, that would be my point of inflection. Okay, it's also possible to have these if we have a breakpoint, so if we're undefined. So that would be something like this. If I've got a vertical asymptote, and I was going up before that vertical asymptote, and now I'm going down. Okay, that's a critical point, because my slope is undefined at that vertical asymptote. Okay, I can also do that with a point of inflection, but only if our concavity actually changes. So, for the example I just had, I was concave up before that vertical asymptote, and I'm concave up after that vertical asymptote. So this is not a point of inflection because my concavity did not change. If I had something like this, so I was concave up, and then after that I am concave down. Okay, this one does count as a point of inflection because my concavity did change. So points of inflection are more specific. They've got more conditions. Your second derivative must change in order to have a point of inflection. That's not true for a critical point. For a critical point, we're looking at first derivative, and even if our slope doesn't change, so if I'm going up and I'm going up afterwards, both of these slopes are increasing, that still counts as a critical point. So both of these are critical points. So yes, critical point, yes, critical point. This is not a point of inflection, but this is a point of inflection, because for this one, our concavity did not change. We're concave up and concave up. For this one, our concavity did change, concave up to concave down.
Okay.
Okay. Then, if I'm looking at my first derivative, we've got a couple more vocabulary items too. Relative extrema is any point that's higher or lower than points around it. So it could look like this or this. This is a relative maximum, this is a relative minimum. Both maximums and minimums are extrema. So the extreme points. It is possible to have infinitely many relative extrema on a function. A sine function and a cosine function both have infinite relative extrema. A relative minimum is a point that's lower than the points around it, so this point is a relative minimum. A relative maximum is a point that's higher than points around it. This point is a relative maximum. Okay, I'm going to take a look at my definition down here. It says my derivative is 0, so the slope is 0. The slope is 0. And my concavity is positive. If my slope is 0 and we are concave up, then I have a relative minimum. The slope is 0 and we are concave up. Okay, for this one, for a relative maximum, my slope is 0 and we are concave down. It would give me a maximum. Okay, are we okay with the first three?
Yes.
Okay. Then for the last two, for absolute minimum and absolute maximum, these do not have to have a slope of 0. It's okay to have a critical point. Critical points, that's a point where the slope is 0 that isn't a minimum or a maximum. But we don't have to have a critical point in order to be the absolute minimum or maximum. This just means the highest or the lowest point. So if I had something like this, come on. Okay, here's my highest point, here's my lowest point, right? None of those had a slope of 0
Yes.
necessarily. But B is still an absolute minimum, and A is still an absolute maximum because they're my highest value and lowest value. The easiest way to find your highest and lowest point is to test all of your critical points and all of your endpoints by plugging them into your original function.
Okay.
Any questions on any vocab?
Oh no.
Okay, Junho, can you tell me what all of the green points are?
Relative maximum.
Perfect. Oliver, what are all the blue points?
Points of inflections.
Right, okay, so we've got points of inflection, relative maximums. Which points are the relative minimums? I'm going to do Oliver again.
D and H.
D and H, okay, perfect. Junho, which point is the absolute minimum?
D.
Not D.
A.
A, perfect. So A is lower than D right now. It's okay for an absolute minimum to not have a slope of 0. So we do need to look at the endpoints as well. Oliver, which point is the absolute maximum?
J.
J, okay. Junho, can you name 2 critical points?
Critical point B, D.
B and D are both critical points. Awesome. And Oliver, can you name 4 relative extrema?
F, H, G, J, D, B.
Okay, you said F, H, J, D, B?
Yeah.
Cool. G is not one, but I think you corrected yourself there, so you're okay. All right. Any questions on anything for today?
No.
No.
All right, so I'm going to take a look at one free response question, and then we're done for tonight. Let's see. Okay, I think I'm just going to do the first one here. Okay, so first part, for part A. I was told that we have this function, natural log x over x, which is true for all x is greater than 0. I cannot plug in x equals 0 at all. The natural log of 0 is undefined. We can't have a natural log of a negative number. The derivative of f is given by f prime is 1 minus ln x over x squared. I want to write an equation for the line tangent to the graph of f at x equals e squared. What's my general form for the equation of a tangent line?
Y minus B equal fx.
That equals...
A.
not fa.
F prime.
Okay, f prime a, there we go. Times
X minus A.
x minus a. Okay, so I need 1 point ab, and then we need to find the derivative at that point. Okay, so I was told what the point should be, x equals e squared. So Oliver, what's my y value for that point?
ln e raised to 2 squared over e squared.
For e squared, okay. So I can use properties of logarithms to break this apart. With my power property of logarithms, this would be 2 times the natural log of e over e squared. The natural log of e will cancel. So that's 2 over e squared. Okay, so I've got our y value. And then I also need a derivative. So I'm going to jump over to Junho for that one. What happens here?
One minus natural log of e squared over e fourth power.
Okay. And again, we can break that apart. So this is With power property, I'll pull my 2 down, so this will be 1 minus 2 ln e. Ln e is 1, so that's just 1 minus 2 over e to the 4th power is negative 1 over e to the 4th power. Okay, and now we just need to put it together in order to get our tangent line.
Where do we get the e to the 4th power?
So my x value is e squared, and my f prime is x squared. So if I square e squared, that'll be e squared times e squared will be e to the 4th power, right?
Yeah.
Okay, cool. So then my final answer would be, I think I'm out of room, so I'm going to give myself another line or so. Okay, final answer is ooh. Y minus b, so that's 2e to the 2 over e squared, equals negative 1 over e to the 4th power times x minus a, x minus e squared. Okay, any questions on part A?
No.
No.
Okay, cool. So for part B, we are looking for the x-coordinate of the critical point of f, and we need to decide whether this is a relative minimum, maximum, or neither, and then justify our answer. What would I have to do in order to get a critical point?
Set the slope to 0.
Okay, either set the slope to 0 or make the slope undefined. So I've got our equation for the slope here. So I'm going to copy that as my first step for B. F prime is 1 minus ln x over x squared. Ooh, that kind of looks like 2 lines. I'm going to rewrite that. 1 minus ln x over x squared. Okay. We were also told that our function is only true for x is greater than 0, so we cannot plug in 0, so we don't have to worry about this function being undefined, since we won't have any negative numbers for our natural log either. So I'm only worried about when will this function be equal to 0 for our critical points. Okay, Oliver, over to you. What do I need to do to solve?
Move the x squared to the other side.
Okay, 0 times anything is still 0, so that's 1 minus natural log x is equal to 0.
Plus 1.
Okay, so I'm going to add...
Plus ln x
Okay,
on the other side.
ln x equals 1. Okay. How can I undo the natural log?
If we both raise it to the e power or something like that.
Perfect, yeah. So I'm going to raise both sides to the power of e. So this is e to the ln x equals e to the first power, or x equals e. Okay, so just to check and make sure, so we've proven that this is a critical point. Is a critical point. But the second part of the question asked, is this a relative minimum, maximum, or neither? And justify your answer. So we can do a first derivative test or a second derivative test. Which do you prefer?
First.
Okay, first derivative test. So I'm going to test points around this value to see what happens around the point x equals e when we plug it into our first derivative. Okay, so if I plug in a number that is less than e, so we'll say natural log 1 is 0. So if I plug in 1, I get 1 minus 0 over 1 is positive. If I plug in a number that is bigger than e, so we'll say natural log of e squared. If I do the natural log of e squared with power property, I can pull that out. So this will be 2 ln e, or 2 times 1. So this is 1 minus 2 on top is negative over something squared will still be negative. Okay, so what is e?
Maximum.
Critical point.
You're both right. E is a critical point, and more specifically, E is a relative maximum. Okay, so x equals E is a relative maximum. As f prime x equals 0 and changes, oops, sorry, f prime, more specifically, f prime at E equals 0 and changes sign from positive to negative. At x equals E. Okay, any questions on how we got the critical point or our justification for relative maximum?
No.
No.
All right, we're good for that one. Part C. We were told that our graph has one point of inflection, and I want to find the x-coordinates of the point of inflection. So before I jump down, how do I find the point of inflection?
The second derive.
Okay, I need to derive twice. Then what?
Set it to 0.
Set it to 0 and solve for x. Okay, or it could be undefined, you're right. There's one more condition though. So what also has to be true to be a point of inflection?
The concavity change.
Perfect. We'll have to test to see if the concavity changes too. Okay, so on part C, I'm going to start with our first derivative from part B. Change colors again. Okay, so our first derivative was 1 minus ln x over x squared. What happens if I derive this? Rewrite that. 1 minus ln x. Okay, what happens if I derive this?
One over.
Okay.
1 over x.
Okay, 1 over x times
X squared minus ln 1 minus ln x times 2x 2x x squared x 4 cubed power to the fourth.
okay,
Fourth power.
x to the fourth power. English is a little weird, so we've got squared, cubed, and then we've run out. So x to the fourth power.
X to the fourth power.
Okay, so I'm going to simplify a little bit. I've got, let me just highlight. Okay, I've got 1x, ooh, it's a little big. Okay, I've got 1x here and 1x here I can cancel. And then I've got an x in this term and an x in this term. So if I factor that out, I can cancel with the bottom. So that'll cancel this x and one of these x's, leaving me with 3 x's on bottom. Okay, any questions on what we did there?
No.
Okay, cool. So I'm going to rewrite this. This is...
But why do we remove an x on the bottom?
because I factored out 1x from the top. I'm going to slow down and do that one more time. So this is... okay, starting here, I've got an x on top and an x on bottom, right?
Yeah.
Okay.
Oh, okay. I see.
Then I can also pull out 1x from both of these terms.
Okay.
And then cancel that with 1x on bottom, right?
Yes.
Okay, cool. So that would leave me with my second derivative is equal to 1 minus ln x times 2 over x cubed. Is, I'm going to multiply first. This is 2 minus 2 ln x cubed. Okay, so my second derivative is 1 minus 2, or negative 1 minus 2 ln x over x cubed. Let's see. I feel like we're missing a sign somewhere.
Isn't plus 2 ln.
We're good there. Okay, up here. If I derive 1 minus ln x, this should be a negative, right?
Oh,
Okay, that's my bad.
yeah.
Negative. And that gives us negative, negative. Okay, so now that's negative 3. Okay, negative 3. I subtracted a negative. This sign's wrong too, actually. Okay. Junho, that's what you were trying to point out, right? Yeah, okay, cool. Alright, so I've got negative 3 plus 2 ln x over x cubed. Double checking really quick. Yeah, okay. My signs look good. So negative 3 plus 2 ln x over x cubed. Now, what do I do in order to find my point of inflection?
Set
Set it to 0.
Set it equal to 0.
Set it to
Okay.
0.
I'm going to make another line over here, I think. So this is 0 is equal to negative 3 plus 2 ln x over x cubed. Junho, I think it's your turn this time. So I need to solve for x.
times x cubed times 3 plus 3 divided by 2. And we rise to the 3 over 2
Okay, that's good. I think I just lost our recording. Oh, no, we're good. Okay. So x is e to the 3 over 2. Okay, to test and see if this is a point of inflection, I need to verify that we're actually going to change concavity here. So I'm going to do a second derivative test. So plugging into our second derivative this time at e to the 3 halves power. Okay, let me zoom out so we can see our function again. If I plug in e to the 3 halves power, the natural log and the e will cancel, so that'll be 3 over 2 times the 2 is 0, so this is negative 3 plus 3 is 0. Okay. If I just plugged in e, then that would be negative 3 plus 2 on top. Would be negative, divided by a positive, because e is positive, cubed. Okay. If I plugged in e to the 10th power, L and E would cancel. I would get 2 times 10 is 20, minus 3 is 17 is positive, and then 10 cubed is also positive. Okay, so what did we just prove?
It is a point of inflection.
That it is a point of inflection. Okay, why is it a point of inflection?
Because the concavity, it's changing from concave down to up.
Perfect. Because the second derivative, f prime prime of x, changes sign. At x equals e to the 3 over 2. Okay, any questions on that one?
No.
Okay. Last one, part D. Ooh, that's fast. Find the limit as x approaches 0 from the right of f of x. Okay, so I just need to copy f of x then is ln x over x. So we want... if I can get this in one page or not. There we go. Okay, we are taking the limit as x approaches 0 from the right of the natural log of x over x, that was f of x. Okay, so if I plug it into the top, what happens to a natural log as we get closer and closer to 0?
Undefined.
What kind of
Oh.
undefined, more specifically?
Vertical asymptote.
Asymptote. Am I approaching positive infinity or negative infinity?
Negative.
Negative.
Negative infinity. Okay, so this is negative infinity on top. And then I'm dividing by 0 plus a little bit. Okay. Dividing by 0 plus a little bit. If I divide by a smaller and smaller number, I'll get bigger and bigger and bigger, right? So that is... I'm going to erase my graph here because I'm out of space. Negative infinity, and then this 1 over 0 plus a little bit is positive infinity, right? So what's negative infinity times positive infinity?
Negative infinity.
Negative infinity. Okay, I'm going to zoom out so we can see everything, and then we'll stop there. Any questions on anything from that free response? Oh, sorry, lost you for a minute. Any questions on anything from that free response?
No.
All right. So that's it for today. I've got 6 free response questions that I've sent in the Skype chat. I want you guys to pick 3 of them and complete them and submit on course sites. Today's homework will be due Friday at 9 in the morning. So that's Friday, 9 a.m.
Okay.
Okay.
All right. Thanks a lot. I'll see you guys on Friday at 10:30 again.